Okay, today we are going to look at permutations. A permutation is an arrangement or listing of objects in which order is important. So I could mow the grass, then go swimming, and then do my homework. Or I could go swimming, then do the mowing, and then do my homework. Notice how mowing and swimming are switched in the second example. This would be two different permutations of the same three events. So you can use the fundamental counting principle to find the number of permutations there would be. Take a look at example 1 on page 766. Julia is scheduling her first 3 classes. Her choices are math, science, and language arts. It says use the fundamental counting principle to find the number of different ways Julia can schedule her first 3 classes. Well, if I think about the fundamental counting principle, which tells me to take the number of possible outcomes for the first event, multiply it times the number of possible outcomes for the second event, and multiply it times the number of possible outcomes for the third event, this is what I end up getting. Class number 1, there are 3 choices of classes to take because she could take math, she could take science, or she could take language arts. So there are 3 choices of classes to take. But when she gets to the second class, she's already scheduled 1 class, so now she only has 2 other classes to choose from. So there are only 2 possible outcomes for the second class. Then when we get to the last class or third class, there's only 1 class left because she'll have already scheduled the other 2. So what actually happens is there's 3 outcomes for choosing the first class, 2 outcomes for choosing the second class, and 1 outcome for choosing the third class. If I'm using the fundamental counting principle, we know we're going to multiply those things together. So I would take 3 times 2 times 1, and I would find that there are 6 different ways that Julia can schedule her first 3 classes. Take a look at example number 2. It says an ice cream shop has 31 flavors. Carlos wants to buy a 3-scoop cone with 3 different flavors. How many cones could he buy if the order of the flavors is important? So let's think about this. If he makes choices for scoop number 1, scoop number 2, and scoop number 3, how many choices would he have for the first scoop? Yeah, there's 31 flavors, so he has 31 choices for that first scoop. How many choices would he have for the second scoop? And remember, he wants 3 different flavors. So can't use the one that he just chose. He would only have 30 choices of flavors. What's he going to do? So few choices to make. And then for that third scoop, well, he only has now 29 different flavors to choose from. So in order to figure out how many different combinations he can make, exactly how many different permutations he can make where order matters in the ice cream flavors, we would have to multiply 31 times 30 times 29, and we would find out he actually has 26,970 possible combinations of ice cream cones that he can make if the order that the ice cream comes in on the cone is important. That's a lot of different choices. That should get you prepared to do letters A and B here on page 766. But we are going to go on to the next page, 767, and take a look at how we're going to write out these permutations. At the top of 767, it says, the symbol P parentheses 31 comma 3 parentheses represents the number of permutations of 31 things taken 3 at a time. So what that actually means is what we just did. There were 31 flavors of ice cream, and we want to look at all the different permutations there would be if I only use 3 of those 31 things at a time. So I'm going to start with 31, multiply it by 30, and then multiply it by 29. So if I go back to the example I just did, down here, instead of putting Baskin Robbins here in front of this, I should be saying permutate 31 flavors of ice cream 3 at a time. And then I would have written this correctly. Up here on this problem, I permutated 3 subjects and I permutated all 3 of them at a time. So that would be 3, 3. This is called a complete permutation. This is called a complete permutation. And there is actually another mathematical symbol that tells me to do 3 times 2 times 1. And that is, I could write 3 exclamation point, which is actually 3 factorial. And when I have a complete permutation of something like this one, I could say that is 3 factorial. And some calculators actually have the exclamation point symbol on them, and you can use that to have it do all the calculation for you, so you don't have to type in 3 times 2 times 1, and which comes in handy if you have to do a complete permutation of a larger number of items. So let's take a look at example 3. This here tells me to find a permutation of 8 items 3 at a time. So I'm going to permutate 8 items 3 at a time, which means I'm going to start with 8 items. There are 8 possible outcomes for the first choice. There are going to be 7 possible outcomes for the second choice, and there are going to be 6 possible outcomes for the third choice. So when I multiply that together, 8 times 7 times 6, I get 336 different permutations of 8 items taken 3 at a time. Let's go on to example number 4. It says find probability. Permutations can be used when finding probabilities of real-world situations. For example, example 4 on the bottom of page 767 says, Ashley's MP3 player has a setting that allows the songs to play in a random order. She has a playlist that contains 7 songs. What is the probability that the MP3 player will randomly play the first 3 songs in order? Well, let's take a look at what it says here. It says, first, find the permutation of 10 things taken 3 at a time. Or, what is a permutation of 10, 3? Well, again, we have 10 choices for that first song. So that would be 10. We have 9 choices for the second song because we're not going to repeat songs. And then we have 8 choices for the third song because, again, we're not going to repeat the first 2 songs. So again, the first number tells me what to start with here. The second number tells me how many places I'm going. So I'm going to take 10 times 9, which is 90, times 8, which is 720 different permutations. Now, if there are 720 different unique permutations where those 10 songs are placed in a different order, how many of those would be song number 1 coming first, song number 2 coming second, and song number 3 coming third? How many of those would be that way? Well, it would just be 1. It would just be 1 out of the 720. So the probability of the first 3 in order equals 1 over 720. A swimming event features 8 swimmers. If each swimmer has an equal likely chance of finishing in the top 2, what is the probability that Yumi will be in the first place and Pakita in second place? Well, let's take a look. First of all, how many swimmers are there? There are 1, 2, 3, 4, 5, 6, 7, 8 swimmers over here in our table. So we're looking for what is a permutation of 8 swimmers. And then we want to know just about first and second place. So we only need to permutate to 2 places. Like on example 4, there are 8 different swimmers who could finish first. After somebody is finished first, there will only be 7 potential swimmers to finish second. So the 8 tells me what to start with. The 2 tells me how many places to go. And then 8 times 7 equals 56. Of those 56 ways that 8 swimmers could finish first or second, how many of those would be with, where are the 2 persons' names? Yumi finishing first and Pakita finishing second. Well, the probability of Yumi then Pakita would be 1 out of 56, because only one of these 56 different permutations of our 8 swimmers to 2 places would be Yumi then Pakita. Pakita then Yumi would be 1, but that wouldn't be putting Yumi first. It would be putting Pakita first and Yumi second. So probability is 1 out of 56. Example F is another problem asking you to permutate a certain number of items to a certain number of places, and then finding the probability of the first 2 items being the ones given. See if you can do that on your own. And then we will come back at the end of class to go over all of the letter problems.